December 16, 1947, at Bell Laboratories in Murray Hill, New Jersey, American physicists John Bardeen, William Shockley, and Walter Brattain invented the transistor. This smaller, less power consuming device, initially aimed at enhancing telephone communications, set the stage for technological advances that would explode from the 1950s onwards. But how did we progress from these electronic innovations to the possible world of quantum computing? The foundation of quantum computing can be traced back to the early development of quantum mechanics in the early 20th century. When Ernest Rutherford bombarded a thin sheet of gold foil in 1909, it gave us the atom and its small dense nucleus at the center, surrounded by mostly empty space with electrons orbiting around it, thus setting the stage for future quantum explorations. While Rutherford's work was foundational for understanding atomic structure, it did not directly address the quantum aspects of atomic behavior. Inspired by Rutherford, Niels Bohr in 1913 proposed his quantum model of the atom, introducing quantized energy levels and electron orbits. This theory laid the groundwork for understanding the atomic and subatomic world as physicists delved deeper into the implications of Bohr's model. They found themselves confronted with the profound questions about the nature of matter and energy. But how did we go from quantum mechanics to quantum computing? In 1900, grappling with blackbody radiation, Planck introduced the revolutionary concept that energy is emitted in discrete units or quanta. This bold hypothesis marked a profound departure from classical physics, suggesting that energy exists in quantized packets rather than as a continuous wave. Planck's quantization of energy laid the foundation for quantum theory, setting the stage for a paradigm shift in our understanding of the physical world. However, it wasn't until Albert Einstein's groundbreaking work on the photoelectric effect in 1905 that the implications of Planck's theory truly began to unfold. Einstein's theory of the photoelectric effect proposed that light consists of discrete packets of energy called photons, and the energy of each photon is directly proportional to its frequency. This concept not only validated Planck's idea of quantized energy but also provided a crucial bridge between classical and quantum physics. By considering light as composed of individual quanta, Einstein's theory reconciled the discrepancies between classical wave theory and experimental observations, laying the groundwork for the development of quantum mechanics. Together, the contributions of Planck and Einstein revolutionized our understanding of the quantum world, paving the way for the emergence of quantum computing and the exploration of its vast potential. Fast forward to the 1920s, a time of great ferment in the world of physics, when Heisenberg formulated matrix mechanics in 1925, a novel approach to quantum theory that dispensed with the traditional notion of particles. This uncertainty principle fundamentally altered our understanding of physical reality, ushering in a new era of quantum mechanics. Meanwhile, in a quiet corner of Austria, Erwin Schrödinger was quietly revolutionizing the field of quantum mechanics. He introduced wave mechanics, a mathematical framework that described particles not as discrete entities but as wave like entities governed by a complex wave equation. These theories, although distinct, provided dual frameworks that enhanced our understanding of quantum phenomena. As quantum mechanics emerged in the early 20th century, only a handful of pioneering scientists delved into the quantum world. The initial explorations by luminaries such as Niels Bohr, Max Planck, and Erwin Schrödinger sparked curiosity and debate. But it wasn't until the arrival of Richard Feynman on the scene that quantum research truly ignited. In his landmark 1981 lecture, Simulating Physics with Computers, Feynman envisioned quantum computers that could simulate quantum phenomena efficiently, exploiting quantum properties like superposition and entanglement. With Feynman's arrival, a surge of interest and investment followed, as researchers from around the world flocked to explore the implications of quantum theory. What began as a niche area of study evolved into a global endeavor, spanning disciplines and fueling unprecedented advances in technology, computation, and our fundamental understanding of the universe. Feynman's impact was profound and enduring, making a pivotal moment in the history of quantum research. He posited that simulating quantum systems on classical computers would become impractical as systems grew, thus highlighting the limitations of classical computing in handling complex quantum simulations. In 1982, Feynman posed a challenge that would later become a cornerstone of quantum computing. He proposed that simulating the behavior of quantum systems using classical computers becomes exponentially complex as the number of quantum particles increases. This insight led to the realization that conventional computers would struggle to efficiently model quantum systems beyond a certain scale, highlighting the need for a new computational paradigm. Building on Feynman's insights, the 1980s and 1990s saw significant theoretical advances. David Deutsch, Peter Shor, and Paul Benioff laid the foundations for quantum algorithms and cryptography, setting the stage for a computational revolution. Today, quantum computing stands as a beacon of scientific innovation poised to redefine computational boundaries. It promises to tackle problems that classical computers find insurmountable, opening new frontiers in fields from medicine to material science. As we delve deeper into this quantum journey, we continue to unravel the mysteries of the universe, one quantum bit at a time.